Good evening. In this video, we're going to talk about proposition 2 from book 3. This proposition states that if we are randomly picking up 2 points on the circumference of a given circle and drawing them together, then the straight line must fall within this circle. So, for example, we are given this circle, and at first let us apply proposition 1 from book 3 we've just proved to find the center of the circle and assume it is point O, and then we randomly pick up 2 points on this circle, for example A and B, and then let us join OA and OB respectively. Okay. The proposition states that if we join AB, then straight line must fall within the circle. So in order to prove it, let us apply the method of contradiction again. So the first step is always to make a hypothesis that is against the proposition. So AB not fall within circle O. Okay, so this hypothesis actually has 2 different scenarios. Scenario 1 is that AB is outside of the circle O, and the second scenario is that AB is on the circumference. Okay, so let's try to prove scenario 1 at first. Scenario 1. So in this scenario, we suppose the straight line AB lies outside of the circle. So let us join AB together here. It looks absolutely weird, but let's assume AB here is a straight line, and let us randomly pick a point on the straight line AB and mark it as point C. Okay. Remember, ACB is a straight line. And then let us join OC together and assume OC is meeting the circumference as a point of D. Correct? Okay. Then from definition 15, we know that radii of the circle are equal. So we know that OA is equal to OB, and if we apply proposition 5 from book 1, we know that in isosceles triangles, the angles that are opposite to equal sides are equal, correct? So they are equal. So the opposite angles means this angle and this angle, they are equal. So angle OAC is equal to angle OBC, correct? And in the next step, please apply proposition 16 from book 1. So the exterior angle of a triangle is always greater than any of the opposite interior triangle. So have a look at this triangle OAC. This is a triangle. So this is an exterior angle of this triangle. Let's mark it as angle 1. So we have angle 1 is always greater than the opposite interior angle, angle OAC, correct? And if we combine these 2 together, we can conclude that angle 1 is also greater than angle OBC, correct? Angle 1 greater than angle OBC. And please pay attention to triangle OCB and apply proposition 19 from book 1. So in a triangle, the greater angle is opposite to greater side. So this angle is greater than this angle, which means the opposite side, OB, must be greater than the opposite side, OC, correct? And we know that from definition 15, we know that OB is equal to OD, correct? And if we combine them together, we can conclude that OD is greater than OC. But we absolutely know that OD is less than OC, correct? It is less than OC. The part is always smaller than the whole. And we can see these two inequalities are contradictory to each other. So they are contradictory, which means our hypothesis here is false, correct? And with a similar method, we can prove the scenario 2 is also false. But please allow me to skip the steps. They are absolutely similar thing. And if we combine them, we can conclude our hypothesis is false, which means our proposition is true. And that's the end of our proof. Okay, thanks for watching. And in the next one, we are going to talk about proposition 3 from book 3. Have a good day.